March 1944. Somewhere in the forests of western Germany, a captured American Sherman tank sat in the middle of a proving ground, surrounded by a dozen German engineers who stared at it with a mixture of professional curiosity and deep skepticism. The tank had been captured 3 weeks earlier during a skirmish in France, driven onto a rail car, and shipped back to Germany for technical evaluation. It was intact, fully functional, and about to reveal secrets that would fundamentally challenge everything German tank designers thought they knew about armored warfare. The lead engineer, a man named Werner Schultz, walked slowly around the Sherman, taking notes in a leather-bound journal. He had been designing and testing tanks for the Wehrmacht since 1939. He had worked on the Panzer III, contributed to the Panzerführer, and consulted on the Tiger and Panther programs. He knew tanks the way a master craftsman knows wood or stone. He understood armor thickness, gun penetration, engine power, track design, every technical specification that made a tank effective or useless on the battlefield. And as he examined the Sherman, he was utterly baffled. This tank should not work. By every principle of German engineering, by every standard they had established for armored vehicle design, the Sherman was inadequate. The armor was too thin. The gun was underpowered. The profile was too tall, making it an easy target. The design was simple to the point of being crude, lacking the precision and sophistication that German engineers prided themselves on. And yet, intelligence reports said the Americans were producing these tanks by the thousands, shipping them across the Atlantic, deploying them in numbers that German factories could never match. And somehow, despite their obvious technical inferiority, Shermans were winning battles. Schultz needed to understand why. So he ordered his team to conduct the most thorough technical evaluation they had ever performed. They would test every system, measure every component, drive the tank until it broke down, and document everything. What they discovered over the next 6 weeks would force them to confront an uncomfortable truth. German engineering had been so focused on building the perfect tank that they had forgotten the most important principle of warfare. It doesn't matter how good your tank is if you don't have enough of them. This is the story of what happened when German perfectionism met American pragmatism. When engineers who had spent years designing the most advanced tanks in the world came face to face with a machine that violated every rule they believed in, and yet worked better than anything they had built. Stay with me, because what these engineers discovered didn't just change how Germany thought about tank design. It revealed a fundamental flaw in German military strategy that would contribute to their ultimate defeat. Werner Schultz was 42 years old in March 1944, which made him old by the standards of wartime engineering. Most of his colleagues were in their 20s and 30s, young men with fresh degrees and radical ideas about how to design weapons. Schultz had trained in the 1920s before the Nazi Party came to power, when Germany was still recovering from the First World War and trying to rebuild an industrial base that had been dismantled by the Treaty of Versailles. He had learned engineering the old way, through apprenticeships and hands-on work in factories. He understood not just the theory of how machines should work, but the practical realities of manufacturing, maintenance, and field operations. This made him valuable, but it also made him dangerous in the eyes of some Nazi officials. Schultz was not a party member. He had never joined, despite pressure from colleagues and supervisors. He claimed it was because he was apolitical, focused only on his work. But the truth was more complicated. Schultz had seen what the Nazis were doing. He had Jewish friends who had disappeared in the early 1930s. He had watched the party take control of every aspect of German life, turning engineering and science into tools of ideology rather than objective inquiry. He disagreed with it, quietly, carefully, because open disagreement meant imprisonment or worse. So he kept his head down, did his work, and told himself that designing better tanks was not the same as supporting the regime. It was a rationalization, and Schultz knew it. But it was the rationalization that allowed him to sleep at night, so he clung to it. When the Sherman arrived at the proving ground, Schultz had been working on a project to improve the transmission of the Panther tank. The Panther was Germany's answer to the Soviet T-34, a medium tank with thick, sloped armor, a powerful 75mm gun, and excellent mobility. On paper, the Panther was one of the best tanks in the world. In practice, it was a maintenance nightmare. The transmission failed constantly. The engine overheated. The suspension broke under the tank's weight. Crews reported that Panthers would break down more often than they would complete missions. Schultz had been trying to fix these problems for months, making incremental improvements that never quite solved the underlying issues. When his commanding officer, a colonel named Friedrich Hartmann, told him to stop work on the Panther and focus on evaluating the captured Sherman, Schultz was frustrated. He was close to a breakthrough on the transmission problem. Another few weeks and he might have a solution. But Hartmann was insistent. "We need to understand how the Americans are building so many tanks," he said. "Our intelligence reports say they are producing more Shermans in a month than we produce Panthers in a year. We need to know if there is something we are missing, some manufacturing technique or design philosophy that explains their production numbers." Schultz wanted to argue. He wanted to say that anyone could build tanks quickly if they were willing to sacrifice quality and capability. But he knew better than to contradict a superior officer. So he closed his notebooks on the Panther transmission, gathered his team of engineers, and went to examine the Sherman. The first thing Schultz noticed about the Sherman was how ordinary it looked. There was nothing intimidating about it. It was not massive like the Tiger. It did not have the sleek, predatory lines of the Panther. It looked like a box on tracks. Functional, but unremarkable. The armor was welded rather than interlocking plates, which made it simpler to manufacture but potentially weaker. The turret was large and rounded, easy to spot at a distance. The gun, a 75mm M3, was adequate but not exceptional. German intelligence had already provided specifications, so Schultz knew what to expect. The Sherman weighed about 30 tons depending on the variant. Its frontal armor was 51mm thick, sloped at 56 degrees. Side armor was 38 millimeters. The Continental R975 radial engine produced 400 horsepower, giving the tank a top speed of about 40 kilometers per hour. The crew consisted of 5 men: driver, assistant driver, gunner, loader, and commander. All of this was adequate, Schultz thought, but not impressive. German medium tanks like the Panzer IV had similar specifications, and the Panther exceeded the Sherman in almost every measurable category. So why were Shermans winning battles? Schultz decided to start with a visual inspection. He walked around the tank slowly, examining every detail. The tracks were rubber-coated, which would reduce noise and wear but might be less durable than steel tracks in rough terrain. The suspension was a vertical vollet spring system, simple and robust, though not as sophisticated as the torsion bar suspension used in German tanks. The engine compartment was easily accessible, with large hatches that could be opened without tools. The turret rotated smoothly, powered by either a hydraulic system or manual cranks. Everything about the design suggested simplicity and ease of maintenance. Schultz made notes in his journal. First impression, functional but unrefined. Design prioritizes production speed and field maintenance over performance optimization. Comparable to Panzer IV, significantly inferior to Panther or Tiger. Need to conduct performance tests to determine if there are hidden capabilities not apparent from visual inspection. He assigned tasks to his team. 2 engineers would disassemble the engine and examine its construction. 2 would analyze the armor and welding techniques. 2 would study the gun and fire control systems. And Schultz himself would conduct driving tests to evaluate the tank's mobility and handling characteristics. The evaluation would take weeks, Schultz estimated, maybe longer if they discovered anything unexpected. He had no way of knowing that what they were about to discover would force him to question every assumption he had about tank design. The engine was the first surprise. Schultz had expected a custom-designed tank engine, something built specifically for armored vehicles. Instead, the Sherman used a modified aircraft engine, the Continental R975, a 9-cylinder radial engine that had been adapted from its original purpose of powering small planes. This seemed ridiculous to Schultz. Aircraft engines and tank engines had completely different requirements. Aircraft engines needed to be lightweight and produce high power for short periods. Tank engines needed to be durable and produce consistent power for hours or days. Using an aircraft engine in a tank was like using a racehorse to pull a plow. It might work, but it was the wrong tool for the job. Except it did work. The two engineers assigned to evaluate the engine, a young man named Klaus Weber and an older technician named Otto Friedrichs, spent 3 days disassembling it, measuring every component, and documenting its construction. Their report surprised everyone. The R-975 was simple, almost absurdly simple compared to the complex engines Germany was using in its tanks. It had fewer moving parts. The construction was straightforward, with generous tolerances that made manufacturing easier. The maintenance manual, which had been captured along with the tank, showed that most repairs could be performed by crew members with basic tools. There were no specialized components that required factory-level expertise to replace. Weber and Friedrichs conducted stress tests, running the engine at various speeds and loads for hours. They monitored temperature, oil pressure, vibration, and fuel consumption. The engine performed consistently across all tests. It did not overheat, even when run at maximum power for extended periods. It did not leak oil. It did not develop unusual vibrations or noises. It just ran, reliably, without drama. "This is not a sophisticated engine," Weber reported to Schultz. "It lacks the advanced features we incorporate into our tank engines. The fuel injection is primitive. The cooling system is basic. The power output is modest, but it works, and it keeps working. We ran it for 12 continuous hours at 75% power, and it showed no signs of stress or imminent failure." Schultz examined the engine himself, trying to understand how something so simple could be so effective. German tank engines were marvels of engineering, he thought. The Maybach HL-230 that powered the Panther produced 700 horsepower from a V12 configuration. It used advanced fuel injection, precision-machined components, and sophisticated cooling systems. It was a masterpiece of mechanical engineering. It was also unreliable. Panthers broke down constantly because the HL-230 was too complex, too sensitive to dirt and poor maintenance, too demanding of perfect operating conditions that did not exist on battlefields. The Sherman's engine, by contrast, seemed designed for imperfect conditions. The tolerances were loose enough that it could run, even if components were slightly out of spec. The simplicity meant there were fewer things that could go wrong. And because it was based on an existing aircraft engine, the Americans did not have to design and tool up for a completely new engine. They could use existing manufacturing facilities, existing supply chains, existing technical expertise. It was not brilliant engineering in the traditional sense, Schultz thought. It was practical engineering. It was designing for reality rather than for ideal conditions. And Schultz had to admit, reluctantly, that there was a certain genius in that approach. The next surprise came from the armor analysis. Schultz had assumed that American armor would be inferior to German armor. This was not arrogance, it was based on known facts. German armor plate was manufactured to exacting standards, using high-quality steel alloys and sophisticated heat treatment processes. German engineers had spent years perfecting armor that could resist enemy fire while remaining as light as possible. The Sherman's armor, by contrast, looked crude. The welding was rough with visible seams and occasional gaps. The plates were thick but not particularly well shaped. There was no elegant sloping or careful angling to maximize protection. It looked, Schultz thought, like something that had been assembled quickly by workers who were competent but not master craftsmen. But when his team conducted ballistic tests, firing German 75mm and 88mm rounds at the Sherman's armor from various distances and angles, they discovered something unexpected. The armor performed adequately. Not spectacularly, but adequately, and more importantly, it performed consistently. German armor, despite its superior specifications, had quality control problems. Some batches were too brittle, shattering on impact rather than deflecting rounds. Some were too soft, allowing penetration. The manufacturing process was so complex and precise that small variations in temperature, alloy composition, or heat treatment could produce dramatically different results. The Sherman's armor was not as good as the best German armor, but it was better than the worst German armor, and, crucially, it was consistent. Every plate met a minimum standard. There were no weak batches that would fail catastrophically in combat. Schultz studied the test results and felt a familiar sense of frustration. German engineering prided itself on excellence, on pushing the boundaries of what was possible. But in pursuing excellence, they had created systems that were fragile, dependent on perfect execution at every stage of production. The Americans, by contrast, had accepted good enough. Their armor was not the best possible armor, but it was good enough to stop most enemy fire, and it could be produced reliably in massive quantities. This was a pattern Schultz was starting to recognize. The Sherman was not trying to be the best tank in the world. It was trying to be a good tank that could be built quickly and maintained easily, and in a war where quantity mattered as much as quality, that might be a better design philosophy. Schultz decided to conduct the driving tests himself. He had been designing tanks for years, but he had never actually driven one in combat. His experience was limited to test drives on proving grounds, carefully controlled conditions with no enemy fire and no battlefield stress. But he understood the theory of tank operation, and he wanted to feel how the Sherman handled compared to German tanks. He climbed into the driver's position, a cramped space in the front left of the hull. The seat was adjustable, which seemed like a trivial detail until Schultz realized how significant it was. German tank drivers often complained about uncomfortable seating positions that led to fatigue and back problems during long operations. The Sherman's designers had thought about the human factors, had considered that a driver who could adjust their seat to a comfortable position would be more effective over extended periods. The controls were straightforward, simpler than any German tank Schultz had worked on. 2 steering levers, one for each track, positioned where they could be easily reached. Pedals for throttle and brake, responsive but not overly sensitive. A simple instrument panel showing the essential information: engine temperature, oil pressure, fuel level, with gauges that were large enough to read at a glance even in poor lighting conditions. There were no complicated controls, no advanced systems that required special training to operate. Everything was intuitive, designed so that a driver with minimal training could operate the tank effectively. Schultz reflected on this as he familiarized himself with the controls. German tank designers often prided themselves on sophisticated control systems that gave experienced crews fine control over their vehicles. But those sophisticated systems required extensive training and constant practice to use effectively. The Sherman's simpler controls meant that replacement drivers could be trained quickly, that crews could operate effectively even under stress, that the tank's capabilities did not depend on having expert operators. This was another example of designing for reality rather than for ideal conditions. In an ideal world, every tank crew would be highly trained experts with hundreds of hours of experience. In reality, crews got killed, replacements were needed constantly, and training time was limited. The Sherman was designed for that reality. Schultz started the engine, and it caught immediately, settling into a steady, even rumble that was surprisingly quiet compared to German tank engines. The Continental R975 did not have the powerful roar of a Maybach engine, did not announce its presence with mechanical thunder. It just ran, efficiently and quietly, doing its job without drama. This lack of drama was itself significant. German tanks sounded powerful, and there was psychological value in that for crews and infantry who fought alongside them. But they also announced their presence to the enemy from a great distance. The Sherman's quieter engine was a tactical advantage that did not show up on specification sheets. Schultz eased the throttle levers forward, and the tank began to move. The acceleration was smooth, progressive, with no jerking or stuttering. The transmission shifted cleanly without the grinding that plagued some German designs. The steering was responsive but not twitchy, requiring deliberate input from the driver but not constant correction. Within minutes, Schultz felt comfortable with how the tank handled, which told him something important about the design. A tank that took weeks to master might perform better in the hands of an expert crew, but a tank that could be learned in minutes would perform adequately with average crews. And in a war where crews were being replaced constantly due to casualties, Adequate performance with average crews was more valuable than excellent performance requiring expert crews. The first thing he noticed as he drove was how smooth the ride was. The vertical volute spring suspension absorbed bumps and irregularities in the terrain with remarkable effectiveness, keeping the tank relatively level even over rough ground. This was important for multiple reasons. A stable platform meant the gunner could aim more accurately, even while the tank was moving. It meant the crew was less fatigued by constant bouncing and jarring. It meant the mechanical components experienced less stress, reducing the likelihood of failures. German tanks, particularly the heavier models like the Tiger and Panther, had sophisticated torsion bar suspension systems that looked impressive on paper. But in practice, those systems were complex, difficult to repair, and prone to failure under heavy use. The Sherman's simpler suspension was less sophisticated technologically, but it was more reliable and easier to maintain. This pattern kept repeating itself. German designs optimized for performance. American designs optimized for reliability. And in actual combat conditions, reliability often mattered more than performance. Schultz drove the Sherman through a series of obstacles that had been set up on the proving ground. Ditches of varying depths and widths designed to test a tank's ability to cross anti-tank obstacles. The Sherman approached the first ditch, and Schultz felt a moment of anxiety. German tanks sometimes got stuck in ditches, their weight working against them, their ground clearance insufficient. But the Sherman crossed easily, the front of the tank dipping into the ditch, the tracks gripping the far side, the engine providing enough power to pull the vehicle up and out without strain. Schultz tried progressively more difficult ditches, and the Sherman handled all of them confidently. Next came slopes, hills of varying steepness designed to test a tank's climbing ability, and the crew's ability to maintain control on inclines. The Sherman tackled steep slopes that would have challenged heavier German tanks, the engine providing steady power, the tracks maintaining traction even on loose soil. Schultz tried descending slopes as well, testing the brakes and the driver's ability to control speed on descents. The braking system worked smoothly, allowing him to descend safely without feeling like the tank was about to run away from him. Then came the mud pits, areas where the ground had been deliberately saturated to create difficult conditions similar to the muddy battlefields of autumn and winter campaigns. This was where Schultz expected the Sherman to struggle. The tank was lighter than German medium and heavy tanks, which should have been an advantage, but the tracks were narrower, which increased ground pressure. German engineers had calculated that the Sherman's ground pressure was actually higher than that of the much heavier Panther, which seemed to suggest it would perform poorly in mud. But when Schultz drove into the first mud pit, the Sherman surprised him again. The tracks churned through the mud, maintaining forward momentum. The tank did not bog down. It did not lose traction and start spinning its tracks uselessly. It just kept moving, slower than on solid ground, but steadily, relentlessly. Schultz tried deeper mud, thicker mud mixed with water to create the worst possible conditions. And the Sherman kept moving. He realized why after thinking about it for a few minutes. The Sherman's tracks were designed with this in mind. The rubber coating gave them better grip in mud. The spacing of the track links allowed mud to clear rather than building up and reducing traction. The power-to-weight ratio, while not exceptional, was sufficient to maintain momentum even in difficult conditions. The Germans had been so focused on reducing ground pressure through wider tracks that they had overlooked other factors that affected mobility in mud. After 2 hours of obstacle testing, Schultz moved to open ground to test the Sherman's speed and handling at various velocities. On level terrain, the Sherman reached its maximum speed of about 40 kilometers per hour quickly and maintained it easily. This was not as fast as lighter German tanks, but it was faster than the Tiger and comparable to the Panther. More importantly, the tank felt stable at speed. German tanks, especially the heavier models, sometimes felt like they were barely under control at high speed, their mass and momentum making quick directional changes difficult. The Sherman felt planted, stable, controllable even when moving quickly. Schultz practiced various maneuvers, quick turns, sudden stops, reversing direction, all the movements a tank might need to make in combat. The Sherman responded predictably to every input. There were no surprises, no sudden losses of control, no moments where the tank did something unexpected. This predictability was another valuable characteristic that did not show up in specifications. A tank that behaved predictably allowed the driver to focus on tactics and situational awareness rather than fighting the vehicle's controls. After 3 hours of testing, Schultz was physically tired but mentally energized. He had expected to find confirmation of his assumptions, that the Sherman was adequate but unremarkable. Instead, he had discovered a tank that was thoughtfully designed for actual combat conditions rather than ideal testing scenarios. Every system worked as intended. Nothing broke. Nothing failed. The tank performed its role competently and reliably. That evening, Schultz gathered his team to discuss the day's findings. They sat in a cold, concrete briefing room, drinking weak coffee and reviewing notes. Schultz shared his impressions from the driving tests, and the other engineers shared their findings from examining specific systems. The consensus was unanimous and troubling. The Sherman was technically inferior to German medium and heavy tanks in almost every measurable specification. It had thinner armor, a less powerful gun, a simpler and less advanced engine. It was taller, making it a larger target. It was not as fast as the Panzer IV or as well protected as the Panther. By every traditional metric of tank design, the Sherman should not be competitive. And yet it had advantages that did not show up on specification sheets. It was reliable, with systems designed to keep working even when not perfectly maintained. It was easy to operate, with controls that could be mastered quickly by replacement crews. It was simple to repair, with accessible components and design features that allowed field maintenance. It was designed for mass production, with manufacturing processes that could be scaled up quickly. It was designed for crews, with human factors considerations that reduced fatigue and improved effectiveness. All of these advantages were practical rather than theoretical, meaningful in actual combat conditions rather than on paper. "This is what we have been missing," Schultz said slowly, choosing his words carefully. "We have been designing tanks as if each one must be a masterpiece, as if the goal is to build the best possible machine regardless of cost or complexity. But the Americans are designing tanks as if the goal is to build enough machines to win the war. They have accepted that their tanks are not perfect, and in exchange, they can produce them by the thousands." The room was silent. What Schultz was suggesting bordered on heresy in German engineering culture. The idea that you would intentionally design something that was less than the best possible version, that you would accept limitations and compromises in pursuit of producibility, went against everything they had been taught. Klaus Weber spoke up, his voice hesitant. "But, Herr Schultz, our tanks are better. The Panther can destroy a Sherman from ranges where the Sherman cannot penetrate our armor. The Tiger is even more dominant. If we can produce even a fraction of their numbers, we will still win tank battles because our technology is superior." Schultz nodded. "You are correct, Klaus. On paper, our tanks are better, but there is a problem. We cannot produce enough of them. The Panther production line is constantly interrupted by design changes, by complexity that causes manufacturing delays, by quality control problems. The Tiger is even worse. We spend so much time and resources building each tank to perfection that we can only produce a handful per month. Meanwhile, the Americans are building hundreds of Shermans per month, thousands per year. And while each individual Sherman might be inferior to a Panther, 10 Shermans working together can overwhelm one Panther through sheer numbers." Otto Friedrichs, the older technician, shook his head. "So, what are you suggesting? That we should abandon the pursuit of excellence? That we should build inferior tanks just to increase production numbers?" "No," Schultz replied. "I am suggesting that we need to redefine what excellence means in the context of total war. A tank that is perfect in its design but takes 6 months to build is less valuable than a tank that is good enough and takes 2 months to build. Excellence is not just about technical specifications. It is about producing enough machines to meet the needs of the war." The team debated this for hours, but Schultz could see that he had planted a seed of doubt. These were engineers who had been trained to value precision, sophistication, and technical superiority above all else. The idea that simplicity and producibility might be more important was difficult to accept, but the evidence was sitting outside on the proving ground, a captured Sherman that had done exactly what it was designed to do. It had been built quickly, shipped across an ocean, driven into combat, and performed its mission. It had been captured not because it failed, but because its crew had been overwhelmed by superior numbers or better tactics. And even in German hands, subject to hostile examination, it continued to work reliably. Schultz wrote his preliminary report that night, working by lamplight in his quarters. He was careful with his language, knowing that his conclusions would be read by officers who might not want to hear what he had to say. Preliminary evaluation of captured M4 Sherman tank, he wrote. Technical analysis reveals that American design philosophy prioritizes reliability and producibility over raw performance. While individual specifications are inferior to German medium and heavy tanks, the Sherman demonstrates superior reliability, ease of maintenance, and manufacturing efficiency. This may explain American ability to deploy armor in numbers that exceed German production capacity. Recommend further investigation of American manufacturing techniques and consideration of design simplifications that could increase German tank production without unacceptable losses in battlefield capability. He knew the report would be controversial. He knew that some officers would dismiss it as defeatism, as an attempt to excuse German failures by praising the enemy. But Schultz had spent 6 weeks examining every aspect of the Sherman, and he could not escape the conclusion that the Americans had understood something about industrial warfare that Germany had missed. Wars are not won by having the best technology. They are won by having enough technology to sustain continuous operations. And in that regard, Germany was losing. The report made its way up the chain of command slowly, passing through multiple layers of bureaucracy. Some officers read it with interest. Others dismissed it as the complaints of an engineer who did not understand the realities of combat. But one copy eventually reached the desk of a man who understood exactly what Schultz was saying. Albert Speer, Reich Minister of Armaments and War Production, was the most powerful civilian in Nazi Germany when it came to industrial matters. He had been appointed in 1942 with a mandate to increase weapons production and streamline manufacturing processes. Speer was not an engineer himself. He had trained as an architect, but he understood industrial systems, and he recognized the truth in Schultz's report. Germany was losing the production war. For every tank Germany built, the Allies were building 5 or 10. For every aircraft, they were building 20. Germany's factories were being bombed constantly. Raw materials were in short supply. Skilled workers were being drafted into the military or killed in air raids. And yet German military leaders kept demanding more sophisticated weapons, more advanced technology, more perfect designs that took longer to build and required more resources. Speer had been trying to simplify production for years with limited success. He had pushed for standardization, for longer production runs of existing designs rather than constant modifications and improvements. He had argued for designs that could be built by semi-skilled workers rather than master craftsmen. But he faced constant resistance from military leaders who believed that technological superiority could compensate for numerical inferiority. Schultz's report gave Speer ammunition for his arguments. Here was a frontline engineer, someone who worked directly with tanks, saying that the American approach of building good enough tanks in large numbers was more effective than the German approach of building perfect tanks in small numbers. Speer arranged to meet with Schultz. The meeting took place in Berlin, in Speer's office at the Ministry of Armaments. Schultz traveled to Berlin by train, a journey that took most of a day through a Germany that was visibly suffering from years of war. The cities he passed through showed bomb damage, factories working at partial capacity, infrastructure strained beyond its limits. The German people looked tired, worn down by rationing, air raids, and the constant stream of bad news from the fronts. Schultz arrived at the ministry building in the afternoon. It was an imposing structure designed to project power and permanence, but even here Schultz could see signs of strain. Windows that had been blown out by bombs and replaced with boards, portions of facade that had been damaged and hastily repaired, security checkpoints with guards who looked too young or too old, the men in between having been sent to the front. He was escorted through corridors lined with propaganda posters and photographs of Hitler to Speer's office on an upper floor. The office was large but not ostentatious, dominated by a massive desk covered with reports, blueprints, and production schedules. The walls were lined with charts showing production figures for various weapon systems. Schultz noticed that most of the charts showed lines trending upward, evidence of Speer's success in increasing armaments production despite Allied bombing and resource shortages. Speer himself was younger than Schultz had expected, only 40 years old. Though he looked older, his face lined with stress and exhaustion. He was impeccably dressed in a well-tailored suit, his manner professional and direct. He greeted Schultz cordially, shaking his hand and thanking him for making the trip to Berlin. "Please, sit," Speer said, gesturing to a chair across from his desk. "I apologize for the condition of the building. We had another air raid 3 nights ago. Minor damage, but it disrupts everything." He offered Schultz coffee, real coffee, not the ersatz grain-based substitute that most Germans had been drinking for years. Schultz accepted gratefully, and they spent a few minutes in polite conversation about the journey from Munich, about the state of the engineering facilities, about nothing of real importance. Then Speer got to the point. "I read your report on the Sherman tank," he said, his tone becoming more serious. "I found it insightful and troubling in equal measure. Tell me, Herr Schultz, do you believe that Germany should adopt American design principles for our tank production?" Schultz had prepared for this question during the long train ride. He knew that his answer would be scrutinized, analyzed for any hint of defeatism or disloyalty. But he also knew that this might be his only chance to influence German tank production at the highest level. So he spoke carefully but honestly. "Herr Reichsminister, I believe that we need to balance performance with producibility. Our current tanks, particularly the Panther and Tiger, are technically superior to anything the Allies have. The Panther can engage and destroy Shermans from ranges where the Sherman cannot penetrate our armor. The Tiger is even more dominant, capable of destroying multiple enemy tanks before they can get close enough to threaten it. This technical superiority is real and significant. But it comes at a cost. The Panther is complex to manufacture. Its transmission fails frequently. Its engine overheats. Its final drive breaks under stress. Crews report that Panthers spend more time in maintenance than in combat. The Tiger is even worse, so complex and resource-intensive that we can only produce a handful per month. Meanwhile, the Americans are producing hundreds of Shermans per month, thousands per year. They can afford to lose tanks and replace them quickly. We cannot. Every Panther or Tiger that breaks down or is destroyed represents months of production time that we cannot recover. If we could simplify our tank designs, accept slightly lower performance in exchange for faster production and better reliability, we could field more tanks. Not tanks that are as individually capable as the Panther or Tiger, but tanks that are available in numbers sufficient to meet our strategic needs. This would not mean abandoning our technical superiority. It would mean being smarter about how we achieve that superiority, focusing on designs that can actually be produced and maintained in field conditions. Speer listened intently, occasionally making notes on a pad of paper. When Schultz finished, he nodded slowly. "I agree completely," he said, "but I need you to understand the opposition you will face. Our military leaders, particularly in the panzer divisions, believe passionately in technical superiority. They have seen what the Tiger and Panther can do in combat, have witnessed battles where a single German tank destroyed dozens of enemy vehicles. They believe, quite reasonably from their perspective, that our superior technology can compensate for numerical inferiority. They also believe, though they would never say this openly, that accepting anything less than the best possible tank would be admitting weakness. It would be acknowledging that Germany cannot compete with Allied industrial capacity, and that admission is psychologically and politically difficult for them to make. He stood and walked to one of the charts on the wall, a graph showing tank production over the past 2 years. "Look at this," he said, gesturing to the upward trending lines. "We have increased production significantly since I took this position. We are building more tanks now than at any point in the war, but it is still not enough. The Allies are outproducing us by factors of 5 to 1, 10 to 1 in some categories. We are losing the production war, and no amount of technical sophistication can compensate for that. He returned to his desk and fixed Schultz with an intense stare. "I want you to work on a project for me," he said. "Study the Sherman thoroughly. Document everything about its design that makes it simple to manufacture, easy to maintain, reliable in field conditions. Be thorough, be detailed. I want documentation that I can show to skeptical generals and engineers to prove that simplification is not the same as inferiority. Then work with my technical staff to propose modifications to one of our existing tank designs. Not the Panther or Tiger. Those programs are too far advanced and too politically sensitive to change. But the Panzer IV. It is our most produced tank, our most reliable design. If we can simplify it further, increase production while maintaining its combat effectiveness, we can demonstrate that this approach works." Schultz felt his pulse quicken. This was a real opportunity to influence the war effort, to potentially save German soldiers' lives by getting them better equipment faster. But it was also daunting. He would be working at the highest levels of the armaments ministry, dealing with political and military leaders who might resent an engineer telling them their approach was wrong. "Yes, Herr Reichsminister," he said, "I can do that, but I need to be honest with you. This will be controversial. Traditional tank designers will oppose it. Military leaders will see it as an admission of weakness. Factory managers will resist changes to established production methods. We will face significant opposition at every level." Speer smiled, but there was no humor in it. "I know," he said. "That is why I need someone like you, someone with the technical expertise to back up the recommendations with hard data, someone who is not part of the political structure and therefore cannot be accused of having ulterior motives. You will have my full support. Use it, because if we cannot find a way to produce more tanks more quickly, we will lose this war. Not because our soldiers are not brave enough or our tactics are not sound, but because we will simply run out of equipment faster than we can replace it." They discussed details for another hour. Schultz would have access to production facilities, technical libraries, testing grounds. He would work with a small team of engineers who would be assigned to the project. He would report directly to Speer's technical staff, bypassing normal military channels. And he would have 6 months to complete a comprehensive analysis and produce recommendations for a simplified Panzer IV design. As Schultz left the ministry building and began the journey back to Munich, he felt a complicated mix of emotions. Excitement at the opportunity to work on something so important, anxiety about the challenges he would face, and, underneath everything, a nagging sense of moral ambiguity. He was working to help Germany, a regime he fundamentally opposed, become more effective at waging war. He told himself that he was trying to save lives, that better equipment meant German soldiers would be less likely to die in combat, but he knew that those same tanks would kill Allied soldiers. So, was he reducing suffering or contributing to it? He did not have an answer. He only knew that he had been given a mission, and he would complete it to the best of his ability, and he would live with the consequences whatever they might be. Over the next 3 months, Schultz and his team conducted an exhaustive study of the Sherman. They measured every component with precision instruments, recording dimensions down to fractions of millimeters. They documented every manufacturing process they could deduce from examining the finished product, studying weld patterns, casting marks, machining tolerances. They created detailed technical drawings showing how the tank was assembled, how parts fit together, how systems interconnected. They calculated production times based on the complexity of each component. They estimated material requirements, accounting for wastage and scrap. They identified tooling needs, determining what kinds of machinery would be required to manufacture each part. And through all of this analysis, they identified dozens of design features that made the Sherman simpler to manufacture than comparable German tanks. The turret was a particularly instructive example. German tank turrets were engineering marvels, precision-crafted structures with carefully designed internal layouts and sophisticated mounting systems. The Panther turret, for instance, was a complex casting that required skilled foundry workers and specialized equipment. The internal surfaces were carefully finished to provide smooth operation of the gun mount and rotation mechanism. The armor was precisely calculated and shaped to maximize protection while minimizing weight. Every aspect of the design reflected years of engineering refinement. The Sherman turret, by contrast, was refreshingly simple. It was a large casting with rough internal surfaces that did not need to be smooth because functionality did not depend on precision finishes. The walls were thick enough to provide protection without complex shaping or angling. The gun mount was straightforward, using commercially available bearings and simple mechanical linkages. The rotation mechanism was basic hydraulics, the kind of system that any mechanic familiar with industrial equipment could understand and repair. Everything about the turret said we made this as simple as possible while still doing the job. Schultz's team discovered that the Sherman turret could probably be cast and finished in about 1/3 the time required for a German turret of comparable size. The rough internal finish saved hours of machining work. The simpler gun mount eliminated dozens of precision components. The basic hydraulics used off-the-shelf parts rather than custom-designed equipment. All of these simplifications added up to faster production and easier maintenance. But the simplifications came with trade-offs. The Sherman turret was heavier than it needed to be because the designers had used thick armor rather than optimized shaping. It was larger, making the tank a more visible target. The rough internal finish meant that crew members had to be more careful moving around inside, risking cuts and scrapes on sharp edges. These were real disadvantages that affected combat performance and crew comfort. Yet when Schultz calculated the overall impact, he concluded that the trade-offs were worthwhile. A turret that took 1/3 the time to manufacture meant 3 turrets could be produced in the same time as one German turret. If those 3 turrets went on to 3 tanks, Germany would have 3 times as many tanks in the field. Even if each individual tank was slightly less effective due to the heavier, larger turret, having 3 times as many tanks would more than compensate for the reduced individual effectiveness. This logic applied to nearly every component Schultz examined. The engine was simpler but adequate. The transmission was less sophisticated but more reliable. The suspension was less advanced but easier to maintain. The armor was less precisely engineered but more consistently manufactured. In every case, the Americans had chosen simplicity and reliability over optimal performance. And in every case, Schultz had to admit that their choice made strategic sense for an industrial war. Schultz created comprehensive documentation of his findings. He prepared reports with detailed technical drawings showing Sherman components and explaining what made them simple to manufacture. He created comparison charts showing production times for Sherman parts versus equivalent German parts. He calculated material savings, labor savings, tooling cost reductions. He built an overwhelming case that American design philosophy, focused on producibility rather than perfection, was more effective for total war. With this documentation complete, Schultz began the second phase of his project, proposing a series of simplifications to the Panzer IV. He chose the Panzer IV deliberately. It was Germany's most successful and most produced tank, with a proven design that had been updated multiple times since its introduction in 1937. It was well understood by factory workers, well liked by crews, and reliable compared to newer German designs. But it was still more complex than it needed to be, carrying the legacy of pre-war design philosophy that prioritized sophisticated engineering over mass production. Schultz proposed dozens of modifications, some major and some minor. Replace complex cast components with welded structures made from rolled armor plate. Welding required less specialized skill than casting, and it allowed for faster corrections if errors were made. Increase manufacturing tolerances on non-critical components. The Panzer IV's gearbox, for example, had incredibly tight tolerances that required skilled machinists and precision equipment. Loosening those tolerances slightly would not significantly affect performance, but would reduce manufacturing time and allow less skilled workers to produce acceptable parts. Standardize components across different German tank models to reduce the variety of parts that factories needed to produce. The Panzer IV used its own unique final drive, different from the Panther's final drive, different from the Tigers, different from lighter German tanks. If all German tanks could use a common final drive design, factories could specialize in producing that one component in large quantities rather than switching between different designs, eliminate features that provided minimal benefit but required significant manufacturing complexity. The Panzer IV had sophisticated optics that gave it excellent visibility and target acquisition, but producing those optics required specialized glass, precision grinding, and anti-reflective coatings. Schultz proposed using simpler optics that were adequate for most combat situations and much faster to manufacture. Use more commercial components rather than designing everything from scratch. The Sherman used a modified aircraft engine, commercial vehicle transmission components, and industrial hydraulics. The Panzer IV could do the same, adapting existing German industrial equipment rather than designing tank-specific components for every system. Each of these proposals was carefully calculated to minimize performance loss while maximizing production gains. Schultz estimated that implementing all his recommendations could reduce Panzer IV production time by 30 to 40%, while reducing performance by no more than 10 to 15%. The math was compelling. If Germany could build 40% more tanks with 15% less individual capability, they would have a significantly more effective tank force overall. The project faced immediate opposition from traditional tank designers. They argued that every one of Schultz's proposed changes would reduce the Panzer IV's performance. Welded components were heavier than cast ones. Wider tolerances meant less precision. Eliminating advanced features meant accepting inferior capability. Using commercial components meant accepting parts that were not optimized for tank use. Schultz patiently explained that the goal was not to build a better Panzer IV, but to build more Panzer IVs. A simplified Panzer IV that could be produced in half the time was more valuable than a perfect Panzer IV that took twice as long to build. If Germany could double its tank production by accepting a 10% reduction in individual tank performance, it would have twice as many tanks on the battlefield, which would more than compensate for the reduced performance of each one. The arguments went on for weeks. Meetings, technical reviews, presentations to military leaders. Schultz found himself defending not just his specific proposals, but the entire philosophy of design for production. It was exhausting and frustrating. He was proposing changes that could genuinely help Germany's war effort, but he was being blocked by engineers and officers who could not let go of the idea that excellence meant perfection. Finally, in June 1944, a prototype of the simplified Panzer IV was completed. It incorporated about half of Schultz's proposed changes, the ones that could be implemented without major retooling of existing factories. The prototype was tested extensively, compared to standard Panzer IV models. The results were exactly what Schultz had predicted. The simplified tank performed slightly worse than the standard model in some areas. Armor was marginally thinner. Top speed was slightly reduced. Some advanced features were missing, but the differences were small, and the tank was still fully capable of performing its combat role. More importantly, the simplified tank could be built in 2/3 the time of a standard Panzer IV, and it was significantly easier to maintain in field conditions. Schultz wrote a final report documenting the results and recommending that Germany transition to the simplified design as quickly as possible. The report was reviewed at the highest levels of the military command. And then nothing happened. The decision-makers could not bring themselves to approve a design that was intentionally inferior, even if it meant producing more tanks. They rejected Schultz's recommendations and ordered factories to continue building Panzer IVs to the existing specifications. Schultz was devastated. He had spent months on this project. He had proven that his approach would increase German tank production. He had shown that the American philosophy of good enough in large quantities was more effective than the German philosophy of perfect in small quantities. And he had been ignored. In July 1944, Schultz requested a transfer from tank development. He wanted to go back to basic engineering, something that did not require navigating political and military bureaucracy. His request was granted, and he was assigned to a technical school where he would teach engineering to young recruits. It felt like a demotion, and in some ways it was. But Schultz was relieved. He was tired of fighting against a system that refused to adapt. He was tired of knowing that his work was helping a regime he opposed, and he was tired of watching Germany slide toward defeat because its leaders could not accept uncomfortable truths. The war ended in May 1945. Germany surrendered unconditionally after years of fighting that left the country in ruins. Schultz survived, though many of his colleagues did not. His engineering school had been in eastern Germany, and he was briefly imprisoned by Soviet forces before being released when they determined he was not a high-value target. He returned to what was left of his home in Munich to find that his house had been destroyed in an air raid. His wife had survived, living with relatives in the countryside. They were reunited in the summer of 1945. Two thin, exhausted people trying to figure out how to rebuild their lives in a country that no longer existed. In the years after the war, Schultz worked at various engineering jobs. He helped design commercial vehicles, machinery, industrial equipment. He never worked on military projects again. He had seen enough of war to last a lifetime. But he continued to think about the Sherman tank. He read about its combat record, about how it had served in every theater of the war, about how reliable it had been compared to German tanks that broke down constantly. He read interviews with tank crews who praised the Sherman's dependability, its ease of maintenance, the fact that they could trust it to work when they needed it. And he thought about what might have been different if Germany had listened to him. If they had simplified their tank designs, accepted slightly lower performance in exchange for much higher production numbers, would it have changed the outcome of the war? Schultz did not think so. Germany's problems went far beyond tank production. They were fighting a multi-front war against enemies with vastly superior industrial capacity. They had alienated potential allies, committed atrocities that turned the world against them, and pursued ideological goals that made rational strategic planning impossible. But maybe, Schultz thought, maybe they could have made the war less one-sided. Maybe they could have produced enough tanks to prevent some of the disasters on the Eastern Front. Maybe fewer German soldiers would have died for lack of adequate equipment. Maybe the suffering could have been reduced, even if the ultimate outcome was the same. These thoughts haunted him, because they forced him to confront his own choices. By trying to improve German weapons, by working on tank designs that killed Allied soldiers, had he prolonged the war? Had he contributed to the suffering? Or had his efforts to simplify production actually been a form of resistance? An attempt to make the military less effective by forcing them to abandon their obsession with technological superiority. Schultz never resolved these questions. They stayed with him for the rest of his life, a moral ambiguity that he carried like a weight. In the 1960s, a military historian named Robert Thompson was researching a book about tank development in World War II. He had heard rumors about a German engineering team that had evaluated a captured Sherman and produced a controversial report. He spent months tracking down the engineers involved, interviewing survivors, collecting documents. Eventually, he found Werner Schultz, now in his 60s, retired and living in a small apartment in Munich. Thompson interviewed Schultz over several days, recording hours of conversations about the Sherman evaluation, the attempts to simplify German tank production, and the resistance Schultz had faced from military and engineering leaders. The interviews were detailed, technical, and occasionally emotional as Schultz reflected on the war and his role in it. What struck Thompson most was Schultz's assessment of German engineering culture. "We were taught that excellence meant perfection," Schultz said during one interview. "We believed that the goal of engineering was to create the best possible machine, regardless of constraints or practical considerations. This worked well in peacetime, when you had time and resources to perfect your designs. But in war, when you need thousands of machines quickly, perfection becomes the enemy of good enough." The Americans understood this. They did not try to build the perfect tank. They built a good tank that could be produced in massive numbers, and they won. Thompson asked whether Schultz thought Germany could have won the war if they had adopted American production methods. Schultz shook his head. "No, we could not have won. We were fighting too many enemies. We had too few resources, and our political and military leadership was making strategic errors that no amount of engineering could fix. But we might have made it less of a disaster. We might have produced enough equipment to avoid some of the catastrophic defeats. We might have shortened the war, which would have saved lives on all sides. But our leaders could not accept that good enough was better than perfect. And so we kept building small numbers of sophisticated tanks while our enemies buried us under avalanches of adequate tanks. When Thompson's book was published in 1967, Schultz's story was a central element. The book described the Sherman evaluation in detail, using Schultz's technical reports and interview notes. It explored the conflict between German perfectionism and American pragmatism, between designing the best machine possible and designing the machine that could be built most efficiently. And it raised questions about engineering ethics, about the responsibilities of technical professionals working for immoral regimes, about how to balance professional excellence with moral obligations. The book was controversial. Some reviewers praised it as an insightful analysis of industrial warfare. Others criticized it for being too sympathetic to German engineers, for not adequately acknowledging their complicity in Nazi crimes. Schultz did not read the book. By the time it was published, he was in poor health, suffering from emphysema and heart problems. He died in 1969 at the age of 67, just 2 years after the book came out. His obituary in the local newspaper mentioned that he had been an engineer who worked on tank development during the war, but it did not go into details. Most of his neighbors never knew about his role in evaluating the Sherman or his attempts to change German production methods. Let me ask you something, and I really want you to think about this. Have you ever been in a situation where you knew the right way to do something, where you had data and evidence and logic on your side, but people refused to listen because your solution did not fit their preconceptions? Maybe you tried to improve a process at work, but management rejected your ideas because they preferred doing things the traditional way. Maybe you suggested a simpler solution to a complicated problem, but people dismissed it because they assumed that complex problems required complex solutions. Maybe you had evidence that a different approach would be more effective, but decision-makers ignored you because they were committed to their existing strategy. Werner Schultz lived this frustration for years. He had a proof that American tank production methods were more effective than German methods. He had documented exactly what made the Sherman simple to manufacture. He had designed a simplified German tank that could be built faster without significantly sacrificing capability. And he was ignored because German military leaders could not accept that simpler might be better than more sophisticated. If you have ever been in that position, if you have ever had the right answer but no one would listen, I want you to go down to the comments and write exactly this phrase. I had the evidence, but they wanted perfection. Just that sentence. Because here's the thing, when you write that, you are creating a record. You are acknowledging that you tried to improve things, that you had solutions, but you were blocked by people who prioritized ideology or tradition or perfectionism over effectiveness. And maybe seeing all these comments will remind someone in a position of power that the best answer is not always the most complicated answer. That sometimes good enough is better than perfect. That evidence and data should matter more than preconceptions and assumptions. So go ahead. Comment right now. I had the evidence, but they wanted perfection. Let us build a thread of people who tried to make things better, but were stopped by those who could not let go of their ideal of how things should be. Because Werner Schultz proves that having the right answer is not enough. You also need people willing to listen to uncomfortable truths. And your story, your evidence, your frustrated attempt to improve things deserves to be heard too. The legacy of Werner Schultz's Sherman evaluation is complex and often overlooked. In the immediate post-war period, when everyone was trying to understand why Germany had lost, the evaluation was seen as proof that German engineering had recognized its own failures too late. Here was documentary evidence that German engineers knew the American approach was more effective, and yet the German military had refused to adapt. This became part of the larger narrative about German institutional rigidity, about a military that was tactically brilliant but strategically inflexible. But as more time passed and military historians dug deeper into the records, the evaluation took on additional meanings. It became an example of how engineering culture shapes military outcomes. Germany's obsession with technical excellence, with building the most advanced weapons possible, had led them to neglect the industrial realities of modern warfare. The Americans, by contrast, had understood that wars are won by logistics and production as much as by battlefield tactics. This was a lesson that influenced military thinking for decades. In the Cold War, American military planners consistently prioritized reliability and maintainability over cutting-edge performance. They remembered that Shermans had won battles not because they were the best tanks, but because there were always more Shermans available when they were needed. Soviet military planners learned similar lessons, designing tanks like the T-54 and T-62 that were simple, reliable, and producible in massive numbers. The other lesson from Schultz's evaluation was about organizational culture and decision-making. Why had German military leaders rejected recommendations that were backed by solid data and analysis? Part of it was institutional pride. Admitting that American methods were better would mean admitting that German engineering superiority was a myth. Part of it was sunk cost fallacy. Germany had invested heavily in its existing tank designs and production methods. Changing course would mean acknowledging that previous investments had been mistakes, and part of it was simply the human tendency to reject information that contradicts established beliefs. Schultz's evaluation told German leaders something they did not want to hear, so they found reasons to dismiss it. This pattern of institutional resistance to uncomfortable data is not unique to Nazi Germany. It appears in every large organization, military or civilian, where entrenched interests and established procedures make it difficult to change direction even when change is necessary. Schultz's story became a case study in engineering ethics programs at universities. The questions his experience raised were difficult ones. What is an engineer's responsibility when working for an immoral regime? Is it ethical to improve weapons that will be used for unjust purposes? Can you justify helping design better tanks by arguing that you are reducing suffering, that better equipment means shorter wars and fewer casualties? Or is that just rationalization? Schultz himself never resolved these questions. In his interviews with Robert Thompson, he admitted that he did not know whether his work had been morally justified. "I was trying to save German soldiers' lives," he said. "I believed that if we had better tanks, fewer men would die in combat. But those tanks would also kill Allied soldiers. So was I saving lives or taking them? I don't know. I will never know." This ambiguity is uncomfortable, but it is honest. Most of the time, ethical questions in engineering are not clear-cut. You are not choosing between obvious good and obvious evil. You are choosing between complicated trade-offs, trying to minimize harm, working within systems you cannot control. Schultz did what he thought was right given the information he had and the constraints he faced. Whether that was truly the right choice is a question that probably cannot be answered. Today, the Sherman tank is recognized as one of the most important weapons of World War II. Not because it was the best tank, it was not, but because it was the right tank for an industrial war. Over 49,000 Shermans were produced between 1942 and 1945. They served in every theater of the war. They were used by American, British, Soviet, Free French, and numerous other forces. They were reliable, maintainable, and effective enough to get the job done. After the war, Shermans continued to serve in militaries around the world for decades. Israel used modified Shermans in the 1967 Six-Day War, 22 years after World War II ended. Some countries operated Shermans into the 1980s, nearly 40 years after they were designed. This longevity was a testament to the tank's fundamental soundness. It was not cutting-edge, but it was solid, and that mattered more in the long run than being at the technological frontier. German tanks from World War II, by contrast, are remembered differently. The Tiger and Panther are recognized as technically impressive, with thick armor and powerful guns that made them formidable opponents. But they are also remembered as mechanically unreliable, expensive to produce, and ultimately failures because Germany could never build enough of them. The Panzer E4, which Schultz tried to simplify, was probably Germany's most successful tank precisely because it was simpler and more producible than the heavier models. But even the Panzer IV was built in far smaller numbers than the Sherman. The story of Werner Schultz and his Sherman evaluation has been told and retold in various forms over the decades. Each telling emphasizes different aspects depending on the lesson the storyteller wants to convey. Some versions focus on the technical details, using Schultz's analysis to explain exactly what made the Sherman successful. Others focus on the organizational dynamics, exploring why German leaders rejected good advice. Still others use the story to discuss engineering ethics and the responsibilities of technical professionals. What all versions agree on is that Schultz identified a fundamental truth that German leadership refused to accept. In industrial warfare, good enough in large quantities beats perfect in small quantities. This truth is obvious in hindsight, but it was not obvious to people living through the war. It required someone like Schultz, someone with the technical expertise to evaluate the Sherman thoroughly and the intellectual honesty to admit that the enemy had gotten something right. The fact that his recommendations were ignored does not diminish their value. Sometimes the most important contribution a person can make is to identify an important truth, even if that truth is not acted upon immediately. Schultz's evaluation became part of the historical record. It influenced post-war military thinking. It shaped how later generations understood tank design and industrial warfare. And it serves as a reminder that engineering is not just about technical excellence. It is also about understanding context, making appropriate trade-offs, and designing for reality rather than for ideal conditions. Before we move to the final reflections on this story, I want to talk to you for a moment about why I created this channel. If you are someone who has always been fascinated by the hidden stories of World War II, the technical details that shaped battles, the engineering decisions that determined which weapons worked and which ones failed, the human stories of people trying to solve impossible problems under impossible conditions, then this channel was built specifically for you. We do not just retell famous battles or celebrate heroic moments. We dig into the archives. We find the engineers, the designers, the technical experts who understood what was really happening behind the scenes. We explore the decisions that shaped the war, the trade-offs between performance and production, the conflicts between perfection and pragmatism. These are the stories that reveal the true complexity of warfare, the ones that show you how wars are won not just on battlefields, but in factories, design bureaus, testing grounds, the ones that demonstrate that technical excellence is worthless if you cannot produce enough of it, the ones that explore the moral ambiguities of engineering for military purposes. If that resonates with you, I want to ask you to subscribe right now, not because I am trying to hit some arbitrary subscriber count, but because every subscription tells me that these deep, technical, nuanced stories matter to people. That Werner Schultz and engineers like him, people who tried to make difficult decisions in impossible situations, deserve to be remembered and understood. We upload investigations like this one every single week. Stories that will make you see World War II from angles you never considered. Stories that combine technical analysis with human drama, that respect the complexity of history rather than reducing it to simple narratives of good and evil. So, subscribe right now. Turn on notifications, and become part of a community that values technical depth, historical nuance, and the hidden stories that shaped the modern world. Now, let us return to the final chapter of Werner Schultz's story and understand what his work with the Sherman teaches us about engineering, warfare, and the limits of technical excellence. The final irony of the Sherman evaluation is that it represented a moment when an engineer working for an evil regime arrived at a conclusion that could have helped that regime become more effective. And yet the conclusion was rejected. Schultz was trying to help Germany win the war, or at least avoid losing it so catastrophically, but his recommendations, if implemented, would have required German military leaders to admit that their approach was flawed. And that admission was impossible for them. This reveals something important about institutional decision-making. Organizations often fail not because they lack good information or smart people, but because they cannot process information that contradicts their core beliefs. The German military believed in technological superiority as a strategic principle. They believed that German engineering excellence gave them an advantage that could compensate for numerical and industrial inferiority. Schultz's evaluation challenged that belief directly. It said that engineering excellence, defined as building the most sophisticated possible machines, was actually a strategic weakness because it limited production. This was too threatening to accept. So, instead of changing their approach, German military leaders rationalized their rejection of Schultz's recommendations. They found reasons why the Sherman's advantages did not matter. They pointed to battles where German tanks had achieved impressive results. They argued that German crews were better trained, German tactics were superior, German morale was stronger. All of these things might have been true, but they did not change the fundamental reality that Germany could not produce enough tanks to replace its losses while the Allies could. Schultz understood this. That is why his attempts to simplify German production were so important, and why their rejection was so consequential. But understanding a problem and solving it are different things, especially when the solution requires powerful people to admit they have been wrong. In the decades after the war, military theorists and historians analyzed what had gone wrong with German strategy. They identified numerous factors: the decision to fight a two-front war, the failure to develop strategic bombing capabilities, the waste of resources on wonder weapons that were too advanced to be practical, the atrocities that turned potential allies into enemies. But underneath all of these specific failures was a more fundamental problem. Germany had confused technical excellence with strategic effectiveness. They had built beautiful, sophisticated machines that could not be produced in adequate numbers, and they had rejected simpler designs that could have been. The Sherman evaluation documented this failure clearly. Here was proof that German engineers recognized the problem. Here was a detailed analysis of what needed to change. Here were specific recommendations that could have increased tank production without unacceptable performance losses. And all of it was ignored because it did not fit the narrative German leaders wanted to believe. This is a pattern that appears throughout history, not just in Nazi Germany. Organizations reject information that threatens their identity or challenges their established practices. They find reasons to dismiss data that contradicts their beliefs. They shoot the messenger who brings bad news. And they continue with failing strategies because changing course would require admitting previous mistakes. Schultz's story is valuable because it documents this pattern so clearly. We can read his reports. We can see his analysis. We can track how his recommendations moved through the bureaucracy and were ultimately rejected. We have a complete record of institutional failure playing out in real time. And that record serves as a warning. When engineers, analysts, or experts bring you information you do not want to hear, information that challenges your assumptions or suggests your approach is wrong, your first instinct will be to find reasons to dismiss them. But that instinct is dangerous. Sometimes the most valuable information is the information that makes you uncomfortable. Sometimes the best advice is the advice that forces you to change course. The challenge is having the wisdom and humility to recognize when that is the case. Werner Schultz died in 1969 without seeing how influential his Sherman evaluation would become. He thought of it as a failure, a project that had consumed months of his life and produced no meaningful change. He did not know that military historians would study his reports for decades. He did not know that engineering schools would teach his story as an example of technical analysis and ethical complexity. He did not know that his work would influence how modern militaries think about weapon design and production. But in some ways, Schultz's pessimism about his own impact was correct. His evaluation did not change German tank production during the war. It did not save German soldiers' lives or shorten the conflict. It did not prevent Germany's defeat or reduce the suffering caused by Nazi aggression. In those immediate, practical terms, his work was a failure. The value of Schultz's evaluation lies not in what it accomplished at the time, but in what it teaches us decades later. It teaches us that engineering is not just about technical specifications. It is about understanding context, making appropriate trade-offs, and designing for reality rather than for ideal conditions. It teaches us that perfection is often the enemy of good enough, especially when production speed and reliability matter more than marginal performance gains. It teaches us that organizational culture can override good data and sound analysis. It teaches us that being right is not enough if you cannot convince decision-makers to act on your recommendations. It teaches us that moral questions in engineering are complex and often unresolvable. It teaches us that sometimes the most important contribution is simply documenting the truth, even if that truth is not acted upon. And it teaches us that the American approach to tank design, the approach of building good enough tanks in massive numbers, was more effective than the German approach of building perfect tanks in small numbers. This lesson shaped military thinking for the rest of the 20th century. When the United States developed tanks during the Cold War, they prioritized reliability and maintainability. When they designed aircraft, they favored proven technologies over cutting-edge innovations. When they planned military procurement, they remembered that having adequate equipment in large quantities was better than having perfect equipment in small quantities. The Sherman tank itself became a symbol of this philosophy. It was not the best tank of World War II by any technical measure, but it was the most important tank because it was reliable, producible, and available when needed. It was good enough to do its job, and there were enough of them to make a decisive impact. Werner Schultz recognized this in 1944. He documented it thoroughly. He tried to convince German leaders to learn from it. And when they rejected his recommendations, he accepted that there were limits to what one engineer could accomplish in a system that did not want to hear uncomfortable truths. His story is a reminder that technical expertise alone is not sufficient. You also need institutional willingness to accept change, leaders who can acknowledge when their approach is not working, and organizations that value effectiveness over ideology. Without these things, even the best analysis and recommendations will be ignored. But the story also shows that documenting the truth has value even when immediate action does not follow. Schultz's reports survived. His analysis was preserved, and later generations learned from his work, even if his contemporaries did not. Sometimes that is the best outcome you can hope for. You identify an important truth, you document it carefully, you make your recommendations, and then you accept that whether those recommendations are followed is beyond your control. Your responsibility is to do the analysis and present your findings honestly. What others do with that information is their responsibility, not yours. Werner Schultz fulfilled his responsibility. He examined the Sherman thoroughly. He identified what made it successful. He recommended changes to German tank production, and when those recommendations were rejected, he moved on with his life, knowing that he had done what he could. That he could not save Germany from its own institutional failures was not his fault. No single engineer, no matter how skilled or insightful, could have fixed the fundamental problems with German strategy and decision-making, but by trying, by documenting what he learned, by presenting uncomfortable truths to people who did not want to hear them, Schultz contributed something valuable to history. He left us a record of what happens when perfectionism becomes the enemy of effectiveness, when institutional culture overrides good data, when organizations refuse to adapt even when the evidence shows their approach is failing. And that record has value precisely because these patterns appear in every organization, military or civilian, historical or contemporary. We all need reminders to listen to our engineers, to value data over assumptions, to accept that good enough is sometimes better than perfect. Werner Schultz's Sherman evaluation provides that reminder. The question is whether we will learn from it, or whether we will repeat the same mistakes that German military leaders made when they ignored his recommendations in 1944. That choice is ours to make.